This is part 2 of our transcendental functions and limits, and we are going to start with analyzing limits of trig functions. So most of the limits that we have done have been polynomials, rational functions, and we just looked at exponential ones. And we've done a few trig ones, and we're going to do some more, and we're going to start with ones where we can do direct substitution, just like we've been doing up to this point. So let's just recap those. So with example 5, it says use direct substitution to find each limit. So you just want to make sure you verify, if you can quickly, that you don't have an indeterminate form like 0 over 0 or infinity over infinity. So we can see that we don't. So we can just go ahead and substitute. So we can do cosine of 2 times pi over 3 divided by pi over 3. And then simplifying, so we're going to have cosine of 2 pi over 3, and I'm going to bring that 3 up from the denominator over pi. So cosine of 2 pi over 3 is going to be 3 times negative 1/2 all over pi. So our final answer is going to be negative 3 over 2 pi. So that's going to be our answer. So doing the same thing with the next one, we don't have a fraction. We're not going to have an indeterminate form. Sine is not a function that has any asymptotes. It is a continuous function, so we don't have to worry about that. So we can do direct substitution. So we get 3 times sine squared of pi over 2, and sine of pi over 2 is 1, so you would be squaring 1, so we get 3. So that's just recapping. We've done some of these direct substitution with trig values already. So again, where we have values that aren't defined in polynomials sometimes, or a rational function, we might still have a limit. So the same thing happens with sine and cosine. And I will tell you this, that you're going to have sine and cosine functions that you have to use many of your identities for. So if you're not up on your trig identities, you might want to go back and look at those. So for this one, it may look a little crazy, and we could direct substitute, but let's, okay, we can direct substitute. I'm thinking of the next one. I apologize. So let's go ahead and do that. We could rewrite this using trig identities, but we'll just do direct substitution. So we're going to have sine of 0 minus 1 over cosine squared of 0. So we're going to have 0 minus 1 over 1 squared. So we get negative 1. Okay. So now, if we look at a graph, like I have here from the Inspire, that does have undefined values, what does it mean that the limit does not exist? Can you look at the graph? But you want to remember that a lot of the questions like this, you are not permitted to use your calculator, and you're not given the graph. So here's where the trig identities come into play. So we're looking at the same function we had before, but what if we're looking at a different point on the graph, one where it might not be defined? So let's simplify this. So we have sine of x minus 1 over cosine squared x. So I am going to use the identity that cosine squared is 1 minus sine squared. Then I'm going to factor, and at the same time in the numerator, I'm going to factor out a negative 1. So the denominator factors into 1 minus sine x times 1 plus sine x. Now I can cancel the 1 minus sine x So I get that our function can be simplified to -1 over 1 plus sine x. So if you look at the original form, if I wanted to use a point like pi over 2, and I substituted in the original equation, I would have had an undefined form. I would have had 0 over 0. But if I use the simplified form from the trig identities, I can substitute it in, and I wouldn't get 0. So the limit exists even if the value of the function doesn't exist. Okay. So let's try to do these 3 examples by using our trig identities, and that could be as simple as a quotient identity, and see how we do on these. Okay, so the first one is the limit of 2 times cosine theta cotangent theta. So we can rewrite this as 2 times the limit as theta approaches pi over 2 of cosine theta times cosine theta over sine theta. So then we have 2 times the limit as theta approaches pi over 2 of cosine squared theta over sine theta. Now I'm going to try a direct substitution, because at this point I don't see anything I can really simplify. So I get 2 times cosine squared of pi over 2 divided by sine of pi over 2. So simplifying that, I get 2 times 0 squared, 0 over 1. So I get 0 for the limit. Okay, next one. I'm going to use another quotient identity. So I'm going to do the limit as theta approaches pi over 4 of sine theta cosine theta over sine theta over cosine theta. And the signs will cancel, and simplifying this fraction, I get the limit as theta approaches pi over 4 of cosine squared theta. Now I can direct substitute, so I'm going to take cosine squared of pi over 4, which is going to give me square root of 2 over 2 squared, which will be 1/2. And then finally the last one, I'm going to use the reciprocal identity for cosecant. So I'm going to take the limit as theta approaches pi of sine theta times 1 over sine theta all over 3 theta. So this simplifies to the limit as theta approaches pi of 1 over 3 theta. And now I can direct substitute, and I get 1 over 3 pi. Okay, so that's how the trig identities are used in terms of algebraic manipulation. Okay, so as you see that with all the limits we've done, we usually have 3 outcomes when we do direct substitution. Our best form is that we get a number value. The 2 forms we'd rather not have is a number over 0 or our indeterminate form, okay, 0 over 0. So remember, things we can do are factor, we can use our identities, and if necessary, we may have to use one-sided limits. For certain trig functions. And our piecewise functions too, things of that nature. Okay, so now we're going to talk about special trig limits. And these are two very important ones that you guys definitely need to memorize. And these were brought up in the last section, section 4, lesson 4. And they came about with the squeeze theorem. So these are, you'll definitely need to memorize these. So we want to make sure we're doing the limit as theta approaches 0. And that's sine theta over theta, and that equals 1. And that also goes for if you have like sine 3 theta over 3 theta. Okay, or sine 5 theta over 5 theta. And same with the cosine one. You want to make sure that the limit is going to 0, and you have 1 minus cosine theta over theta, and that's going to equal 0. These two limits you definitely need to memorize. They come about from the squeeze theorem, and they are ones that are considered, you just have to know, like knowing, like tangent is sine over cosine, one of those kind of things. Okay, so what I'm going to do is, we're supposed to use a graphing calculator for next example, and this is where we're going to look at the limits from the left and the right because they're in undefined forms, and see if we can figure out what the limits are. So what I'm going to do is I'm going to pause the video, and I am just going to go ahead and fill in the table. Please remember that you need to have your calculator in radian mode in order to do trig functions in calculus. Okay, so here's the table filled in, and if you had trouble getting these values, please ask in class. So what we can see here is if we're taking the limit as theta approaches 0 for every one of these, we can see from the left and from the right that this function is headed towards the value of 2. So for the next one, the limit of cosine 3 theta minus 1 over theta as theta approaches 0, what you can see is from the left we're getting smaller, and also going towards the right we're getting smaller, and we're headed towards 0. For the third one, we are headed towards the same value. We're getting very close to 0.75 on both sides, so we're getting very close to 3/4. And then finally the last one is like the second one, the cosine one. We're getting very small as we come from the left and very small as we come from the right, so we're headed to 0 again. So you can always use the table if you have your calculator and look at the left and right limits. So that's all I'm going to do in this video, and I will finish the section in the last video.